computer. Okay, share screen. And of course, okay, so first thing I'm going to do is review the assignment, and I hope you guys tried it earnestly. And if there's something that wasn't clear, just please ask me now while I'm reviewing it. Don't feel shy, and don't worry about your classmates. I'm pretty sure they probably have the same question. So, okay, so I gave you, I think, yeah, I believe I gave you two problems. The first problem was we have a W310 by 143. Now, I don't know if you guys can appreciate this, but this is one hell of a column, okay? A W310, let me just, hold on a second. I want to annotate also. So I have a W310 by 143, 350W. Okay, so this was the old Canadian steel. I didn't modify my assignment, but it doesn't matter. So like I said, these profiles, these are no longer milled in Canada, and therefore most likely you'll be stuck with an American one. So this would be slightly lower. Now, the steel column has a length of 7,600 millimeters, and the weak axis is literally supported. So what this means is that in plan view, okay, remember in plan view, this is your Y flange. Okay, always remember this is your strong axis and this is your weak axis, and therefore what we're saying is that this one is being braced somewhere. So in other words, it's the weak axis that's prevented from moving side to side. The long one can move out of its plane. So
Sir,
that, yes.
sorry, can I stop you there? On my paper, I have 9,500 millimeters.
Yeah, that's what I was about to say right now too.
Oh, okay. So I guess this is a typo. And is a brace at 4,500?
Yeah, the brace is the same.
The price is the same, but
Okay, so this is a typo. Sorry about that. Let me, okay, so I have 9,500. Okay, so 9,500. Sorry about that. Maybe hopefully I used the, okay, so sorry about that. I guess I should have checked. Okay, now the column is pinned, so 9,500. I'll keep that in mind. If anything, I'll just correct myself as I go along. But the CR, okay, so the column is pinned at each end. Determine the factor compressible CR using 4 point, the table, and the W columns. Okay, so when you're using this table here, guys, I can tell you right now, when you're using this table here, you don't have to worry about checking whether you meet the classifications of the requirements for a class for the compression. That's already incorporated in the table. But when you're using this table here, you have to check to make sure that the member falls within that category. So that's all I'm going to say here. So now, first thing I'm going to do is I have a W310 by 143. And of course, I go to this W sections here, and I go and find all the values I need to do my calculations. In other words, I go get the RX value. So W310 by, okay, so W310 by 143. So I have it right here. So this is where I get all the values. I get my cross-sectional area, I get my RX, my RY, and then on the next page, I get all the values to check. This here, just so that you guys understand how these tables work. Okay, the reason why they give you this D minus 2T, well, that's really the H. So now all they're doing here, they're actually giving you the H of the web. Okay, so the D minus 2T value is the H of the web that you use to do the calculation of H over W. And of course, the B is what you use because the BEL is half of the B. So and therefore I need the T, the W, the H, and the, like I need the web, the thickness, and I need the small W here, and so on. So I come here, I get the values, and so I get a cross-sectional area 18,200 square millimeters. I get my RX value, I get my R value. Like I said, the H is the D minus the 2T value, okay, and this is the thickness of the web, so it's that going to be divided by that. And then, of course, the B is the total width of the flange, and therefore this is the T. So I check for the local buckling requirements according to table 1. And of course, I go to this table, and this is where I find, okay, so for element support along one edge, of course, you know, like if you notice that what they mean is that if you look at here, okay, this element here is only supported along one edge, this edge here. So therefore, and then it even tells you your flanges of I section, T sections, and channels. So you would have to use this one here. And then for web support at both edges. Okay, so in other words, this is the one plate element here, one plate element here. So therefore, this one would be supported at both edges. Okay, so therefore you would use this value here. So that's what they mean by element support at one edge as opposed to, and so on. Okay, so clear. Oops. So here H over W, which is what I got from the table, that has to be less than that ratio of 670 divided by the square root of the strength of your steel. And of course you have 19.8, here I get 35.8, so far so good. And then for the flanges, I take half of B, which gives me the BE, okay? BEL divided by 2. Take the thickness of the flange, this is 6.7. This is 10.7, I'm okay. So that means I meet the requirements of table 1, therefore I can use table 4.4. And guys, in my spreadsheets, when we're going to be doing the columns, the exterior columns, I built this into the spreadsheet, but this is something you should assure yourself. Don't just blind, either use, if you're ever designing columns, either use this table here, and if you're going to be using this table here for whatever reason, make sure you do this check. This is important because that table is only valid for this condition, okay? Keep that in mind. So now, therefore, we can use table 4.4, okay? Now, the slenderness ratio. So I get KL is 5,000. Okay, yeah, so it was a typo in my problem because I used 9,500. That's what I gave you in a problem, right? Okay. Now,
Yeah, that's
do you understand why KL is 5,000? Because I have, like, it's 9,500. I said it was only braced at 4,500. Therefore, the longer one that's unbraced is 5,000. Okay, I want you to be careful about that. I think that's why I did this. I modified it because I wanted you guys to realize that when you're looking at your column, okay, when you're looking at your column, okay, here's my column, and all of a sudden I have a brace here, okay? If you always take the longer of the two as being the unbraced length, and then the longer of the two here with respect to KLY is 5,000, okay? That's why I did that, so that, so now, KL over RX, okay? I check the slenderness ratio. This is always called the slenderness ratio. It comes up to 69. And of course, in structural steel, we cannot exceed the 200. And I'll keep, you know, so I do want to see this when you're doing your solving your problems to remind you that the maximum slenderness ratio in steel is 200 as opposed to wood, which is only 50. And KL over RY, of course, is 63.3, and therefore it's always the one, the larger of the two that will govern the capacity of the column, and in this case, it's this one. Now, once I've got my KL over X, or my KL over R, in other words, it's the L over RX value, okay? I can go straight to the table, right? So table 4.4 to obtain the value of the unit. So I get the CR over A value from the table, okay?
Sir,
Yes.
quick, can you re-explain how you got the KLY is equal to 5,000?
Well, it's
Please.
because we said that the problem said that the column has a height of, this is the total height of the column. We said that the total height of the column is 9,500. That's what we said, all right?
Okay.
Okay.
Yeah.
And we said that it was laterally braced at 4,500.
Oh, I get it. I get it. Okay.
Okay, and that's why you have to be careful because you have to realize that I tell you that it's braced there, therefore it's the longer of the two. You understand?
I get it. Yeah.
So this comes. So you got to watch which, like, and that's I didn't want to trick you, but I wanted you to understand that you have to be careful. Always take the longer unbraced length to do your calculations. Okay, now you get it. Okay,
Yeah. Thank you.
good, no problem. Okay, So now, of course, with the value of this, of course, I can go get the KL over R value here. You know, like I put KL over R value, but I think that, yeah, I have 69, and of course, I know the strength of my steel. That's all I need to do. Those are the two no fixed variables I need to have when I go to table 4.4. So I can get, the table gives me this value. In other words, it gives me the CR over A value is equal to that, okay? So, okay, so if I go to this table here, I have 69 and 350. Now, you see, so it goes up to 200, and therefore I go to 69, go to 69 here, go across, and you'll notice that this is a Canadian steel handbook, okay? And because the steel that is produced in Canada had a strength of 350, that's why they have this column here in bold, okay? So that's why they bolded this one. Otherwise, if you're using the American one, feel free to use the 345. That's what 50 KSI is, 344.5. It's one and the same, okay? So here I go get my CR over A value of 203 MPa, okay? Because here it even tells you CR over A in MPa, those are the units. And there's a little asterisk to remember this is an MPa. So now that I get that value, I can simply go back, and so I get my CR over A of an MPa, and of course, be careful. This is newtons per millimeter squared. This is millimeter squared. So this times this gives it to me in newtons. And we don't work in newtons when we're talking about columns. We work in kilonewtons. So remember to divide it by 1,000. Okay. So in other words, this gives it to me in kilonewtons. I get 3,695 kilonewtons. Is that okay with everybody? Did I make any more typos? Please let me know.
All good, sir.
Okay.
Sir, I just have a quick question.
Yeah, go ahead.
If we meet the slenderness ratio, if we meet the criteria to use table 4.4, we don't have to calculate the CR by hand with like the whole
no,
formula. We could just skip it and use a table.
Exactly. So what the table
Okay.
does, what the table does for you, Gordon, is it takes that ugly equation. You see, remember the equation, right?
Yeah.
I'm trying. Okay, off the top of my head, I could almost write it on. You know, it takes the phi FYA. What is it? Lambda 1 minus lambda 2. Anyways, it takes that ugly equation, and it gives you the value of that, because what it does is that if you look at that equation, all you need to know in that equation is the length, okay, and you get and the slenderness ratio and all that, and therefore the only thing that they don't have, that table can do for you, is give you the area of the column. So therefore they're calculating that whole equation without the area. That's what they're doing in this table.
Oh, okay.
So for example, you take that equation, take out the A value out of that equation, and all the other variables that are in that equation are calculated in that table. And that's why once I go to that table, I just have to multiply by my cross-sectional area. It gives me my CR value.
Okay. Yeah.
And keep in mind, I want to go back and keep in mind, okay? And like I said, and something else I want to stress here, okay? So, and it talks about it here. We talked about this very quickly, but okay, this is for rolled sections, okay? That's why the N, so in this table, it used the value of 1.34. There's also table 4-5, which I didn't give you, but that's when you're using welded wide flange sections, when you're using class H. Okay, there's another table where they use N equal to 2.24, but I didn't give you that table because, you know, very rarely are you guys going to be using welded wide flanges, and you should never specify class HSSs, okay? In other words, hot rolled HSSs. They're very hard to find, and as a matter of fact, I'm going to stress that you should always use the American ones, because that's what most people try to get away with. And so not to get into trouble, always design with the American HSSs. And that's what we're going to be doing in this whole class. Okay, so there. Okay, so there you go. Okay, that's why I just wanted to stress that. So now that I've got this table, okay, I want you to use the W column. I call it W columns. Okay, this is a table where you don't have to worry about meeting the requirements of table 1 because this table incorporates that, okay? So here I have a KL over LY of 5,000. And I have an KX over LX of 9,500. Now, the thing is that that table, what you have to keep in mind is that table is always based on the radius of gyration with respect to the IX value, okay? And therefore, when this is the one that governs your design, you have to find an equivalent KL LY, an equivalent KL over LY, okay? And guys, it's just, it looks, it might look complicated, but if you understand math fairly well, you realize what we're doing here. The equivalent KY-LY for KLX-LX, you simply divide the LX value by the ratio of RX over RY. So all you're doing is that you're taking away the RY value in that table and you're replacing it by RX. That's all you're really doing, okay? So you're just mathematically manipulating the table here, okay? So it doesn't, so as soon as the KX-LX is the one that governs your design and you want to use the table, you cannot go straight to the table. You shouldn't be using this value here because you're going to be grossly underestimating the capacity of your column, okay? So therefore, KY-LY, okay? See, so therefore, because this is longer, because this equivalent length here is still longer than this one, then this one governs, okay? Now, of course, if this thing was embraced and KLY was 9,000, we'll automatically go straight to the tables. But if you have a braced column about the Y and you have to check to see which of the two is going to govern, and therefore in this case, this is the one that governs because it's still longer than that one. So therefore, now I can still go to the table, but I go to the table with this value here. I do not go to the table with this value here because this is the equivalent value of L with respect to the Rx value. So that's what the table does. Now, if I go to the table, so what did I have? I don't remember the column. The column was a W300 by 143, I guess. I don't remember. Anyways. So basically, when I come here, I'm looking for, okay, so these are all done. The whole table is done. When they say the KL value here, this is all done with respect to RY, okay? So this is all done with RY. And if you want to find that RX over RY ratio, I mean, you get it from the table, but you can also get it here. Here's all the RX over all, this is they give you the ratio here if you want, okay? It's also in that table. So if you don't have, if you have this table here, so now I'm looking for a W310 by 143. So I go from 310 by 143. Not there yet. Oh, here we go. So here we go, 143. So now I'm looking for at least, what was the length? 5,000. What was the length of our column? 5,500. Can anybody tell me what the length we're looking for?
It's 5,398 millimeters.
Okay, so in other words, we're here. We agree? In other words, you always go get a length slightly longer than what you need or what you have, and therefore, this is where we go get the CR value right there. Okay, so we have a CR value of 3,630 kilonewtons, and that should be very close or the same as what we calculate with table 4.4. And so that's where we get that. And like I said, if you come down here and you want to looking for your RX or R1.76, you have it right there. Or if you already have your RX value, already have your RY value, well, if you take those two, you'll still get the same value as you have in the table right here, okay? So you have some of these sectional properties, okay, here for all these shapes. And so for KL of 5,500, the CR is 3,630. And I think that's what we got. What did we get with the other table? 3,695. So you can tell that the other one's a little bit more accurate. I mean, because you're rounding off a little bit more, but you're in the same ballpark.
So, sir, I have a question.
Yeah.
About that CR. So, which in like real life, which one would we use? Would we do our design with 3,695, or could we use the 3,630? I know it's a small difference, but
it's like it's up to you. You understand? You know that, for example, this is the actual length that you have, right? When you went to the table, you had to use 5,500. Okay. And therefore, because you used something slightly longer, it lowered your CR. So out of the two, the other table is giving you a more accurate result. Do you follow? That's why, like the other one gave me 3,006. What was the other value? 3,600 and? Did anybody
94.6? Is it that one?
94. Okay, so 90. You understand? So look that slight length increase of 100 millimeters, right? Fair enough. It lowered my CR value. Now the other thing is that the other table we use 350 MPa. That's another factor in the other table. Okay, when we use table 4.4, we use 350. When we came to this table here, it only used 345. So those are the two variables that made you lower the CR value. So if you understand that, then you can feel very confident of using the first value. You understand? It's up to you. So
okay, thanks.
You see, because the whole table, this whole table here, because they throw in the American steel, the Canadian steel, they, instead of calculating everything with 350, they calculated everything with 345. And because they know it'll be good for the 350. That's all they're doing. Okay. So I'm almost sure that if you want to do the math, take just to see, like 360, right, times 350 over 345, just to see how much that already increases your value, right? I'll do it right now. 3 times 350 divided by 345. That already increased it up to 368. You see, just the fact that they're using a weaker steel. And then the fact that we're using a longer length here, you understand? So that's where the differences come in. But guys, keep in mind, as long as you're in the same ballpark, that's what's important, okay? If one table gives you 3,600, the other one gives you 2,800, well, something's wrong somewhere. That's where you should go double check why, okay? But if you're in the same order of magnitude, you're doing okay, okay? And ultimately, if you want, you can just take the formula, you can program it in an Excel spreadsheet, and therefore when you go there, all of a sudden, you can have the whole thing calculated for you by the Excel spreadsheet, and therefore it'll be even the most accurate value because you're using the formula, if you want to do it that way. It's up to you. Okay, so I hope you guys got the answer. Now here, determine the lightest size square HSS. Now here I'm telling you to use American steel, and in real life, guys, always use the American steel to do your calculation. This way, if they happen to give you some Canadian steel, it's only going to be stronger. And if they give you the best Canadian steel, it's only going to be that much stronger. So I've been involved in a case where they specified the Canadian HSSs, okay? And the person slipped the American HSSs. It became a big claim, okay? And of course, I mean, it's like you might not be responsible, this and that, but you're going to get dragged into it. So you might as well just use the American steel. That's what everybody's using because it's cheaper to buy, and it's, that's what a lot of the fabricators are using. So use when we use the HSSs, use the American one, and you'll see. Okay, now here I have a dead load of 2.0 kPa, a snow load, okay? Now remember the live load reduction factor, okay? If I exceed 20 square meters, right, I'm allowed using a live load, okay, but you're not allowed using it for snow. Therefore, you're not allowed using that equation, okay? So keep that in mind. That's a live load reduction factor. It's only for your occupancy loads. Any snow load, no matter what size your tributary area, you cannot reduce it. Now the unsupported length of my column is 6 meters. Okay, column effectively pinned at both ends. That means my K is equal to 1.0. That's all that tells me. Okay, and therefore now, so all I have to worry about, what I mean by 40 square meters, that here's my column here. And of course, that means I have, you know, this way between the two supporting members, I have 20 meters. And in this way between the two supporting members, I have 20 meters. And I'm sorry, 40. Anyways, like I probably have, sorry, I have like 5 meters or 8 meters, and that gives me an area of 40 square meters. I was going to 400, sorry. So that's what I mean by the tributary area. Now, the only thing I ask you to do is find the lightest one, okay? And guys, you're going to go to the tables. What I like to do is when I go to the tables, okay? Okay, this is, okay, so first I factor my loads. Now, you notice like I didn't bother putting load combination 1 because I know in this case here that this is the one that's going to govern. So right away I put that in. If you explain to me why you didn't do load combination 1, I won't mark it wrong. If you don't do it, I'll mark it wrong. And the reason why I should explain here that since the dead load doesn't exceed 10 times the snow load, it's going to be load combination 2 that's going to govern. So here's my factored load. And then of course my PF is very quick, okay? Or in this case I use CF because it's steel. Okay, CF is equal to the factored load times the tributary area. I have a CF value of 316 kilonewtons. I have a length of 6 meters. Now, the only other thing is I gotta know which grade and which class of steel I'm gonna be using. So if when I go to the tables, okay, my design objective is to make sure my CR is greater than my CF. Now I go to HSSs and I tell you to use a square one. Now, when I gave you this table, and like I said, I apologize for the quality. I scanned this at school on the printer. And like I said, if we go to the very beginning, okay. So the way it works, okay, the way it works is that this is the Canadian G40.21 350W. That's your Canadian steel, okay. That's your Canadian one. And unfortunately, if you had the handbook, you would see a C here. Okay, the C means it's a class C. It's a class C. What that means is that this HSS was cold formed. They took a plate of steel. Okay, they took a plate of steel. They took a plate of steel like this, and they actually bent it into this shape here. And then they seam welded all along. So they took this and they made this out of it. That's what they mean by cold formed. And because the bending creates residual stresses, it's not as strong as the hot form. Okay, so that's what they mean by cold form. So this gets bent into this. You like that? Okay, and that's what they're doing. So now they start off with the class C, and of course this is the grade, the grade of steel, and the class, the strength of your steel. So, oh, sorry. Now, they start off with the rectangular ones, and then they move over to the square ones, and then they move over to the round ones. And then once you finish with the round ones, okay, then they go with the class H. Now, this is the best. This is the strongest HSS. In other words, they're extruded cold, hot. In other words, they get pushed through an extrusion thing and they come out already in that shape. And because they're hot, they have less residual stresses. And therefore, this is the one that's got the highest strength for the same steel, for the same cross-sectional area. This is the one that has the highest strength or the highest resistance. And the same thing, like here, I don't know if you see it, but you have a H there. And the same thing. And of course, the ones that the fabricators try to pass on you all the time are, okay. Now, don't confuse grade C with class C. Grade C is an American, okay? So grade is not class. So this is ASTM A500, okay? In other words, this has FY of 345. In other words, it's 50 KSI, okay? And this is the one I'm asking you to choose from, and therefore you would come to this part of the table here. And all you're doing basically, what I like to do in this table, this is what I do, okay? Hold on a second, I'm trying to find, okay? This is what I'm looking for. I start with the length, and then I go down until I find a CR value greater than my CF value. Okay, so here you can see that the CR values are very high, so this is very, very strong. So I just keep going. I'm just trying to find my mouse here. So I keep going with 6,000 until I find a CR value that's at least 316. Look, this, oh, here, I got one, 305, okay? 350. So I might consider using a HSS. Oh, I told you to use a square one, first of all. So let's go look for the square ones. Okay, let's get to the square ones, okay? So here we are at the square ones, still very high. Now, we start getting into the HSSs. Now, the way you can decide which is the lightest one, okay, it's very simple for me, but so that you guys can see this. Okay, like I said, I worry about the length, and then once I have the length of my column, I go across, okay? So I come here and I look for a CR value that is greater than, so here, I got one here. There's one CR value, okay? And this tells me the mass per, and this tells me how much it weighs. So, and here I've got 344. Here's another one, okay? And this one is lighter than that one. So in other words, I have to look across the table until I find, so this is pretty light here, 152 by 152 by 217. And then I list the one, and then I look for a CR value of 316 here. This is 324, and therefore that is pretty high. So out of these three, I guess, and I'm not trying to get as close as possible. I mean, I'm trying to make sure I'm over my CF value, but I'm looking also like, which is the one that is the lightest. That weighs a little bit more than that one. And that one definitely weighs more than that one. And of course, if I go to the next page, I probably don't even have a CR value that fits there, okay? So there you go. So that's how you basically look at it. So you look, once you start getting into the range of your CR values greater than your CF values, like I said, you only work along this line here because your length is 6 meters, and therefore that's how you choose. And guys, write them down. Write down your three choices, and then look up here, 21.7, 28.4, 37.2. Oops, no, sorry. And so I come back here. So I have 152 by 152 by 4.3. I have a CR value of 344, and I have a CF value of 316. Is that clear, guys? Okay, so if I tell you to choose the lightest, like look at, once you start getting into that range, they're all going to be about there. So you just go up, look at the one that's got the lightest mass per unit length, and that's going to be the lightest one, as long as your CR value is greater than your CF value. Is that clear to everybody?
Yes, thank
Are we
you.
good? I hope you guys got that answer, okay? Okay, so now that we've talked about columns, and I mean, they're not that complicated because they're fairly easy to analyze in terms of getting what they have to resist and so on. And once you know how to use the tables, they're very easy to design. And this is my assignment number 3. I should go correct. Anyways, I might not even use these slides ever again. So, okay, so let me close this now. Okay, today we're going to talk about base plates, because once you design your column, the next thing you're going to have to worry about is sizing a base plate so that it can transfer the load properly to your foundations, okay? And therefore, we'll talk about base plates, and they're not that complicated, but I want you guys to understand. Now, these base plates, okay, some people like to call these, I think they call these, like base plates are grouped into 3 categories, okay? In other words, this is the very first category, is the simplest category, okay? And some people like to call this case number 1, okay? Case number 1 is very simple, okay? This is your CF. You notice the CF coincides with the centroid of your column, right? And therefore, you don't have any eccentricity. And therefore, case number 1 is that you're assuming that the pressure exerted by your foundations, whether it's a wall or a footing or a pilaster column, you're assuming that it's uniformly, you have a uniform pressure developing underneath the column. So that's case number one, okay? Case number two is when you start getting historicity, we will be doing that for our project. I will be giving you spreadsheets to do those calculations. They become quite a little bit more involved, and you'll see that we'll do them together. I won't even ask you. I'm just going to show you how to do them, more for your general information. So when you have an interior column where there's no wind and everything's pin connected and everything's nicely, there's no eccentricity. In other words, this is my column here, like this, in plan view. Okay, and of course, this is, this is, okay. So in other words, what we're saying is that the load is falling right there, okay? And that's what happens, and therefore everything underneath is nice. It's assumed to be nicely uniform. Is that clear to everybody? Okay. So that's number one. Now, see here, they're showing you, these are, some people like to call these anchor bolts. Some people like to call them anchor rods. I like to call them anchor rods because I like to use rods to anchor my columns. Some people like to use anchor bolts, but so there's two things. They're both correct. It all depends whether it's a rod or is it a bolt. Rods are weaker than bolts, so therefore they have a different resistance value. But here, what they're showing you is that they have one here and one here. So that's where your anchor rods or bolts will go. And most likely this is no longer allowed, okay? Because what happened was that they were erecting this steel structure and there was only 2 bolts on this column, okay? And as the worker was climbing up the column collapsed and he died. The column fell on him and he died, okay? So now, whenever you're designing anchor bolts or anchor rods, you need a minimum of 4. You cannot put only 2 anymore. You're not allowed using 2. So it's always minimum of 4 anchor bolts or anchor rods, whether it's you need them or not. It's more for erection purposes. And ever since that worker died, that became the new standard. So this is an old picture from an old book, and that's no good anymore, okay? What they should actually be showing, they should be showing 4 anchor bolts or anchor rods. Keep that in mind, guys, okay? Okay, so everybody understands? Now, of course, TP is what you're also, well, first of all, you're trying to determine the size of your plate. That's fairly easy because it all depends on the bearing resistance of your concrete. And you then after, once you've calculated this, the size, you want to calculate the thickness, okay? And basically, I want to talk about this here, okay? I don't know if you can see it, but all you're really doing, you see here, from here to here, how this plate cantilevers from the column. So all this does is that it creates a bending moment here, okay? And therefore you're calculating the bending moment that's created there, and therefore you know that MR, okay, is equal to phi Z Fy. And as long as, and that's the Z of the plate, and as long as the MR here is greater than the MF that's happening there, you've designed the thickness of your plate. That's what you're actually doing, okay? So, okay, now, so here you go. Let's start with, okay. For base plates subjected to vertical gravity loads only, the following assumptions and design methods are recommended, okay? This is, and again, you make certain assumptions, okay? The factored gravity load is assumed uniformly distributed over the base area within a rectangle of 0.9 D. Now, D is always the depth of your column, and B is always the width of your column. We've seen this, okay? So, and then what they're saying here is that within this area here, okay, within this area here, when you look at the pressures, you assume them to be uniform, just like we saw in the other pictures. And that's an assumption because in theory, some areas are a little bit higher than others, but you assume that it's uniform, okay? The base plates exert uniform pressures over the footings, and that's, that's what you're doing. The base plate projections beyond the, in other words, this area here, these projections here, okay, act as cantilevers subjected to a uniform bearing pressure. And that's what we're going to be doing. So in other words, you're basically this, here's my plate here, like this, okay, here's my column, okay, you're exerting a pressure here, okay, and therefore I just need to calculate the moment at that point there of this cantilever. I don't worry about this inside here, okay. This is where it becomes critical, and therefore I'm calculating the thickness based on the moment that I'm exerting at that point there. And of course, now, so CF is the total factored load, right? A, of course, is the area of your column. And remember, B, always use B for this side and use C for D. Okay, so A is B times D. TP is the thickness of the plate. Okay, FY is the minimum yield strength of base plates. Now, guys, plates, I don't know, I haven't checked, but plates, the strength of steel for plates is normally 300 MPa. Okay. I'm going to still use 300 MPa. I don't know if they started producing plates with 350 MPa. I know they started producing angles with 350 because even angles were only produced with only 300 MPa. So if anything, we'll use 300. And if you find out that they're producing plates with 350, I mean, you can change the FY to 350, but we'll be designing all our plates based on FY equal to 300, okay, as opposed to what we have for 345 or 350 for the W sections. Now, this you've seen, FC prime is the strength of your concrete, right? And of course, this doesn't change. In other words, this is the resistance factor for structural steel, whether it's plates, whether it's W section, it's a resistance factor. You're taking the nominal, okay, the nominal strength of your steel of 350, and you're reducing it by 10%. So you can get what they call a factored resistance. And that's what that is, okay? Does anybody have any questions regarding this diagram here? I want you guys to look at this diagram and realize, okay, so when we're looking at the variable N, okay, N is the length of the cantilever with respect to the B dimension, and we're looking at the M. M is the length of the cantilever with respect to the C dimension. And of course, this is based on, okay, and you notice here they take 0.95. In other words, they still leave a little bit of this thing to be cantilevered, and here they still assume this part to be cantilevered. So that's why you only take 80% of B. They still assume that this is cantilevered here, okay? And that's what they're doing, okay? They're just being a little bit more conservative. So that's, I want you to, relate to these variables here, because we are going to be using these. You'll see these in the equations, and I want you to be able to relate to this. So is that clear? This is clear enough? Okay. So now we have, okay, determine the required area A. So basically what you're doing is you're taking your axial compression force, okay, your CF, and you divide it by the bearing resistance of the concrete. So in other words, what you're doing is you're taking the CF is coming down here, okay? And what's pushing up to keep it in balance or to make sure it doesn't go through your concrete, okay, it's the BR of the concrete. And that's equal to 0.85 phi CFC prime. And I think we've seen this last year in reinforced concrete when it came to bearing, okay? So here, the bearing of the concrete is assumed to be 0.85 FC prime. It will, of course, phi C 0.65. Okay, that you should remember from last year. And that's how you calculate the area required. That makes sense. So therefore, it's the strength of your concrete that's going to determine how much of a surface of the concrete is going to be needed in order to be able to resist the force that's coming down. Now, the projections B and C, so that the maximum M and N, okay, beyond the plane should approximately equal. Now, I'm going to teach you, or I'm going to show you how you're going to optimize and make sure that they are approximately equal, okay? So you first start off by designing a square plate, and then we will optimize the plate, and we will make these approximately equal. So determine, then once you determine the value of M and N, then you can actually determine the value of P. And here's the formula, okay? Now, these formulas are complicated. not really. I mean, they're not complicated at all. CF over BC, that gives you the force that's acting under this value here, divided by these two values gives you this value here, okay? And anyways, I don't want to complicate you, but I can show you how easy that this, how they derived the TP value. Now, of course, if it's the biggest cantilever, whether it's the M or the N, that will, the longer the cantilever, the bigger the bending moment. Therefore, that's going to determine the thickness of the plate. So you have to check which one of the two is the biggest, and you use the bigger one. That's all they're saying here. Now, these formulas were derived by multiplying the factor moment acting at the portion of the plate taken as a cantilever to the factor. There you go. So in other words, they calculated the moment here. So here's my column. Here's my pressures. And of course, these are based on, this is basically 0.85. They calculated the MF here at that point there based on the cantilever, and they made sure that the MR value of the plate was greater than this value here, and that's all they did. Now, to minimize deflection of the base plate, the thickness should generally not be less than 1/5 of the overhang. So we will always check that to make sure that the length M or M is, like, in other words, the thickness is greater than 1/5 of M or N. Okay, and that will, I'll show you how to do that in the calculations. So there you go. So that's what we're going to be using to calculate our thickness, one of these two, depending whether it's M or N, okay, the greater of. And of course, okay, so the best way to kind of put this into perspective, of course, is to do an example. And here's a good example, okay. So we have a W310 by 118. I got to write this down. W310 by 118, okay. Okay, subject to a factored axial compression load of 2,500 kilonewtons. I don't know if you guys can appreciate this, but that's a lot of quarter pounders, okay? That's about, that's over, anyway, that's a lot of quarter pounders sitting on top of that column. Subjected to a concrete strength, okay, so here the concrete has a strength of 20 MPa. And guys, don't be surprised, a lot of foundations, they do use 20 MPa to do the foundations because, sometimes they have to be oversized for geometric reasons, and therefore, since they have to be designed, and therefore, it's very, using 20 MPa for your foundations is not out of the, okay. Design the base plate assuming the steel has 300 MPa. Like I said, I'm still going to use 300 MPa until, the industry starts producing them at 350. I will always assume that my steel plates are done at 300. Okay, so now, what do I need to do? Okay, of course, I need to be able to calculate the area required. Okay, so I go to my W shapes and I start looking for the, it's a W310 by, sorry, clear the drawing. So I'm looking for a W310 by 143. So here I am, 310 by 143. So I'm here, okay. So what I want to do is I want to go get B and D from the table. Okay, so I go to the next page. So I go get my B and my D value because I'm going to need those in order to calculate my N and my M values. Okay, so I get those from the table. And of course, okay, so the B value is 307 and the D value is 314. And I think that's what we had before, if I'm not mistaken. Let me just make sure that W3. Yeah, there you go, 3, okay. Just to make sure we're on the same page. And now, what's the area required? Well, like I said, you take your CF value. Now, guys, be careful. Remember, this is in kilonewtons. Remember that this is in newtons. So either divide this by 1,000 or multiply this by 1,000. Just be careful about that, okay? And therefore, this is the area required based on the bearing resistance of the concrete. This is 0.85 phi C FC prime. Okay, that's what that is. Now, Of course, the simplest thing to do, okay, is to make sure that, okay, we can start off by making a square plate, okay? So try B is equal to C. So if I want to make a square plate, all I got to do is take the square root of this, okay? So I take the square root of this, okay? And then I get an area, as long as my area is greater than what the area required, I'm okay. So I take the square root of that. And guys, when you're sizing plates, use multiples of 10, okay? In other words, 480, 490, 500. Don't use 485, don't use 481. Use multiples of 10, okay? Do yourself a favor. Do not go below multiples of 10 when you're sizing the area of your plate. When it comes to the thickness, you'll have no choice because there are certain thicknesses of plates, and you'll see that later. But as far as the areas, use multiples of 10. Now, determine M and N. Now, of course, now that I got my B and my C value, and I got my B, small b, and my D value, okay, I can then use those, okay. 0.95 D. So in other words, I take D here of 314. This gives me 298. And of course, M is equal to 148 minus 2, okay, divided by 2. So I have 191 millimeters projecting. So if I look, if you remember the drawing before, so here is my column, right? And this was the M value here. So here the M value is 91 millimeters. All they're doing is they take the overall length width of the here, okay? Subtract this here, which is 0.95 D, and then divide it by 2. That's all they're doing, okay? And then, so that's for the, now, with respect to B, I have 117. So what they're saying here is that this one, oops, sorry. This one here, it's 117. Of course, it's 117 on that side, and it's 117 on that side. And it's the bigger cantilever that governs, therefore, this is what's going to govern the thickness of the plate. So once I determine which one is the bigger one, then it's very simple. All I need to do now is go to the formula and calculate. Okay, sorry, I can't even see what's written there because this thing popped up in my face. Okay, use N for your design. Of course, use the larger of the two. And now I just go here. I've got all my variables. And again, guys, okay, be careful about here. Okay, what I like to do is when it comes to the steel, what I like to do is when I do this calculation, I simply put 0.3 here. In other words, I put 0.3 kilonewtons per millimeter squared for Fy. By putting 0.3 here, I've automatically divided by 1,000, and therefore I've got the right units because this is in kilonewtons. That cancels that. And now I got 33.2. Now, when it comes to steel plates, okay, when it comes to steel plates, okay, they are produced in certain thicknesses. Now we'll look at this the first time you've seen this table, so I'm going to go through it a little slower. Is it clear to everybody, or do you want me to spread it out? Should I spread it out? Is that better?
Yes, good things.
It's better, okay. So, and then I'll shrink it after. So guys, this here is very simple, okay. You have nominal thicknesses. The nominal means the overall thickness. Nominal thickness here, of course, you can see how thin this is, okay? But then all of a sudden you start getting into, okay? Now you have first preferences, second preference. First preference is simple. That's the one that's more readily available, but it doesn't mean that you can't get the second one, but God knows when it's gonna get produced, who's got it in stock, and so on and so on. So whenever you're designing something, for example, if I need a 13 millimeter plate, I can specify as a second preference a 14 millimeter plate, but if they can't find a 14 millimeter plate, then go use a 16. That's what so you'll see in all my solutions, I put my first prep and my second preference. If there's, okay, for example, if I would require a 15 millimeter plate, then I would simply put 16 millimeter because that's my first preference. There's no, but if I have a 30 millimeter plate, I would always on my drawing put second preference 14 millimeters, first preference 16. Because if they put a 16, it'd definitely be good for a 14. So that's what they mean here. First preference, second preference. And here they also give you how much, okay, these things actually weigh, okay? So in other words, the mass per square millimeters, okay? And of course, that's for the mass, and if you want to know the dead load, this just converts this into kilonewtons, okay? So that's how this works. So as soon as you determine your thickness, so let's say I got a thickness of 27 millimeters, that's, or 27.2. So I come here, 27.2, oh, I'm here. So I can put 28 as my second preference and 30 as my first preference. And that's what I would choose in terms of a plate and so on. Now, if I have a 34 millimeter thickness, I would say first preference, I would simply put 35 millimeter. End of story, okay? So if I happen to fall somewhere in between these two, I can always specify my drawing as a second preference what I want, and then you should always say my first preference 30 millimeter. And you let the guy go through the trouble of either finding a 28 millimeter plate if he wants to save a few bucks, or he'll just order 30 and he'll use 30 to fabricate his steel. Okay, so that's how these tables work. They're not that complicated. It's just to know what are the available thicknesses, the nominal thicknesses that are available in the market. You know, like you'll notice that there's no 17, there's no 27, you know, like, so don't specify 17, don't specify 27. There aren't any, okay? So these are the nominal thickness that you will be able to find, and these are more readily available than these are. So now, so that's pretty clear. Now, what we had a thickness of 30. Do you remember the thickness that we're looking for in our problem? Does anybody remember? I guess we'll go back. We need 33.2. Okay, so there we go. So we need 33.2. So we know that we are here somewhere. Okay, 33, we're here, and therefore I would just simply specify a 35 millimeter plate. Okay. And guys, you should appreciate that. That's starting to be a significant thickness, okay? So that's what I would specify, 35 millimeter plate. And there you go. So I come here. Now here, I don't like this. I copied this straight out of my handbook. I don't like what they do here. They check here that, you know, n over 5 for deflection. You need, you know, you shouldn't, it should be at least 23.4 millimeters thick. I'm using 33.2, therefore I'm using 35. It's okay. Okay. I mean, if you're using 35, it should be 35 here. It shouldn't be 33.2. Now, okay, so that's simple, straightforward. You take a square plate, you calculate the area. In other words, the A required, you simply take the CF divided by the, you know, 0.85, the bearing resistance BR, you get your area required, take the square root, round it up, you know, round it up to multiples of 10. There's your square plate. Calculate your N and your M. In that case, when it's square, most likely it's always going to be your N that's going to govern over your M, all depending on your B value and so on. So, and you basically design your plate. That is fast, that is easy, that is straightforward. Now, they say that they recommend to make the N and the M value as close as possible, so therefore the cantilever will be the same on both sides of the, you know, on both sides of the column. And therefore, that's called optimization. And now I'm going to show you how you do that, because it's good to know. And we're going to learn how to optimize. It's not that complicated. It's just a bit of more mathematics, and that's all it is. So optimization for the base plate. Okay. Now, how do we optimize a base plate? Well, we said, okay, the area is B times C. Okay. Now, we know that the area in this case was 2020. This is the area required according to, remember, this is what we had. In other words, when we took the CF over 0.85 phi C FC prime, we ended up getting, this is the area required, not the area, okay, this is the area required. Now, we know that this is how you calculate the B. In other words, you take 2N plus 0.85 B, the width of the column, and 2M 0.95 D, I'm sorry, the width of the flange and the depth of the wide flange. Now, so this is how I calculate my B and my C. So now what I can do is simply put all of these into this equation here, right? So I put all of these in this equation here. So I have 226,000 is equal to, you know, B times C. And of course, for me to get the best possible size, what do I want to do? I want to make sure that And now I know the value of B, we got that from before. I know the value of D, we got that from before. So I have these two variables. And of course, now I still have two unknowns in here. Okay, so basically what I want to do is I want to come up with only one equation, one unknown, and I know I can solve for it. So therefore, what I want to do, I'm going to replace the B and the D by the values I have. Now, for optimization, it said that we should try to make N and M as close as possible. Well, in this case, what we're going to do is, okay.
Sir,
Yes.
for the value of n, didn't we get the value of n like just above there, the 35? Isn't that?
Yeah, but that's because we've already had a B and a C value.
Oh, we can't use that then. Oh.
No, in other words, this area here was the area based on CF over 0.855 CFC prime.
Yeah.
You see what I'm saying?
Yeah.
So all I have here is an area, and I know that that area is B times C. You agree?
Yes.
You see?
I agree.
And I know that the value of B, this is how I calculate my B value. This is how I calculate my C value.
I see. Okay.
Okay, that clear? Okay.
This is like more specific, like more detailed. Like.
Well, no, what I'm doing now is, like they said, the best possible thing is to have the N and the M value approximately the same.
Yeah, agreed.
So
Okay,
now
understood.
I am mathematically manipulating this equation so I can get the N and the M value almost the same.
But in real life, does it make a big difference?
Oh yeah,
or-
yeah, you'll see the savings. And that's
Okay.
what we're going to see at the very end of this problem. You understand? Okay,
Okay. Thank you.
fair enough. So let's go through the problem. And in real life, yes, I mean, if you want to be lazy, just design a square and what do you care? But if you want to save some money, this is the way you do it, okay? So now, so basically to optimize, you let N equal to M, or you let N equal, so let's let, okay, to optimize, N is equal to M. So therefore let N is equal to M. Now, we take the N out and we replace it by M. So now we've got one equation, one unknown. Hey, we're getting somewhere, okay? And therefore, unfortunately, this ends up being what? A quadratic equation, right? Everybody remembers how to do this? In other words, you take this, multiply by this, you take that, multiply that, Everybody remembers how to expand this equation? I hope you do. Does anybody have any problems with this? Now's the time, guys, to review your math even. Does anybody have any problems with this? We're all good? Okay, so now that I've got this quadratic equation, 4m squared plus 1.85m, and of course I bring this to this side, becomes a negative, is equal to 0. How do I solve a quadratic equation?
Quadratic formula.
Exactly. That's where we get the quadratic formula. And I'm sure you guys all remember the quadratic formula at the tip of your fingers, minus b plus or minus b squared minus 4ac over 2a. We all remember that, right? At the tip of your fingers. Now, I know some of you on your calculators, you have the quadratic formula that you can use to put in your calculators. That's a very good way of using it, okay? And of course, here's a quadratic equation. Minus b plus or minus the square root. And of course, if you remember, I hope you all remember this, okay? This is the value of a here. This is the value of b. And of course, that's the value of c, okay? So that's all you have to remember. And you have to remember how the quadratic equation is meant. So therefore, you end up getting two roots. I don't know if you guys still call them roots. In other words, where it crosses the x-axis, and that's what this equation gives you, okay? So you use the quadratic equation, and we start solving for it. So therefore, I get minus plus or minus put in all the values. I'm not going to go through all this, and hopefully I get m equal to n 102. Okay, so now that's what it should be, right? In other words, the n and the m value should be approximately 102 millimeters. So now I'm going to take this number, put it back into those equations, and get the value of b and c. All right, so I get the value of 2 times this, okay, and that gives me the value of b. Now, like I said, use multiples of 10. So therefore, I won't use 449.6. I will use 450 for b. And as far as c goes, I take the same thing, 102, 0.95, I get 502, I'm gonna round it up to a multiple of 10. So in other words, I'm not gonna use 502.3, and that's not what I'm gonna specify in my drawing, I'm gonna specify 510 millimeters. So that's gonna be the value of C. So now that I got this, I should, in theory, recalculate my M value, because I'm not using, like, in other words, you notice it went up slightly here to 106, okay? I need to recalculate my M value because this is the one that's going to govern my design, okay? I mean, I can go calculate the N, but I can tell you the N is going to be very close to 102. So I recalculate my M value. So that's the one that governs my design. And now, of course, now that I got my M value and I got my CF value and I got my A value, I got my, sorry, B value and my C value, I can simply go ahead and calculate my thickness. So now the thickness of the plate is equal to 2 times C, the same formula, times CF, M squared in this case, because that's the one that governs. B times C I know, phi I know, Fy I know, and of course I take the square root of it. That's, I'm sorry, I should have written out the formula here, but so here I go. 2 times 2,500, okay, kilonewtons, times C of 106, which we just calculated, divided by 450, which was the value of B, 510, which was the value of C, 0.9 is the value of phi. Like I said, I always put this to 0.3, so this cancels this right away, that cancels that right away, blah, blah, blah. And of course, so here we go. And therefore, I do this calculation, end up with 30.1 millimeters. Now, guys, don't get religious, okay? I will now go to the table, okay? And I know that I'm not gonna go, I'm gonna be, you know, like, it's not for 0.1 millimeters, I'm gonna worry about it. I am actually going to take this value here, okay? So I'm going to use a 30.1 millimeters, guys, with all the assumptions that we do in these calculations. That would be, okay, that would be good enough, okay? So if you're within 30.1, 30.2, use 30. You don't have to go to 32. You should always use something greater than what you calculated, but in this case here, I would use 30, not a problem. So that's what I'm going to be using, 30 millimeters. So my first preference is 30 millimeters, and since I don't have a second preference, I won't even write it down. Now, check deflection. Of course, the deflection has to be m over 5, 106 divided by 5, and it's less than 30, I'm okay. So my deflection's in check, my thickness is good. Now, who asked me if it's worth doing this? Omar, was
Yeah,
it you?
me, it's
Omar,
worth it,
okay.
yeah.
Well, what you do is, remember the area of how much steel was saved?
The area, I remember the
Well, it's gonna come up, but you understand what we're doing now? Like, what we're doing is that we're gonna go take the first plate, the first area, and calculate how much mass that was. We'll take this plate and by the thickness, and then we'll divide the two, and we'll see how much we save. So
Okay.
so in other words, if I go back, right, I'll go here to show you that, you know, where do you get the mass per area? It's all in here. So you know, you have to remember that this is 236. The other plate we had was a number 35. This is 275. Okay, so that's where you get those values. So basically, I have a 35 millimeter plate is 275, and if you remember, the area was 480 by 480. So I have 63.36 kilograms, right? And of course, 30 by plate is 233, and this was a 45. We said it was 450 by 510. Okay, so what do we save? We save 9.2 kilograms. What do you think, Omar?
Yeah, per one, yeah. If you have like 10 of them.
Exactly. That's how you have to look at it. So when you have a big warehouse and if they all have the same, you know, they have basically the same, and you multiply that. So you can, you know, don't forget, this is kilograms. So in other words, that's almost 20 pounds of steel. You understand? And I couldn't believe, I found out that just the material these days is going for $1. Just the material is being sold at $1.50 a pound. So that means that they must be doing structural steel for about $4,000 a ton. Wow. And there you go. So was it worth optimizing? Yes. Okay. And therefore, like Omar said, and like if you have 100 of these columns, well, you know, you saved over a ton of steel, and therefore you probably save $3,000. So that's how you have to look at it, but it is the right thing to do. And guys, it's not that hard. And well, how are we doing time-wise? No, we're doing great. Okay. Does anybody have any questions on this before I move on? It's all good?
Yeah. Sir, actually, I have a question. Sorry.
Yeah, go ahead.
When you drive the bolt or the rod, do you make a hole in the plate or beside it? You just and then
Oh,
you
it's
weld
always,
it.
you'll see there's edge distances that you have to respect. Okay. It's always inside the plate.
Okay.
Okay. And that's where when we get to the lab, well, I'll talk to you about sometimes, and it's the geometry that will dictate the size of your plate. It's not even these calculations. And we'll do that in the lab. Okay. So, so keep in mind, like, for example, here, I forgot, what did we get in terms of the size of plate? We ended up getting, what was the size? What was the M value that we had? Does anybody remember? I don't know.
102 or 106. You fixed it.
106, right?
Yeah.
So we have about 106 millimeters here, right? So that's ample to put the two bolts, one there, with the column there. Okay, and when we get into when we get into bolts and stuff, there's minimum edge distances that you have to provide when you do these bolt holes, and we'll do that when we get into connections, depending on whether it's sheared off or whether it's cut off with a, so, and 102, you should leave at least 35 millimeters there. Okay, so therefore we would have ample space in 102 to be able to put those bolts there. Okay, so the bolt holes are always done inside the plate. Now, if you can also put them here, but I prefer putting them on the outside just in case there's a bit of rocking. This is better out here. Okay.
And do they come from the manufacturing,
Well,
the fabricator?
just no, like with the fabricator, for example, well, whoever's doing the concrete, right? He'd have to order he's the one that's going to make sure that he orders his anchor rods or his anchor bolts, so that he can put them in the concrete, right?
No,
When
I
he's,
mean like the holes. When you have the holes, who makes the holes?
oh,
Like
the fabricator, the steel
Oh,
fabricator.
okay.
Okay, the steel fabricator will make the holes inside the. They got drills, you understand? Zzz, zzz, and they just drill a hole in the plates, you understand? So some of them have depending on the equipment that they have. Okay, so some of them have drills, some of them have like these super sophisticated lasers, that can actually cut the plate, and they can actually flame. I don't know, but it's done by the fabricator. If that's what you're asking me. Okay, so that was one problem where we had a wide flange as a column. Now, when we have a square HSS, it should be a little bit simpler. Why? Why should a square HSS be simpler than a wide flange?
Not sure actually.
Well, I mean, if you use a square plate and you got a square HSS, you need to optimize.
It's gonna be all the same.
Exactly. N and M are going to be the same, so you don't need to optimize. Okay. So now the only thing I want you to keep in mind, okay, when it comes to a square HSS, okay, so you have a HSS that's 203 by 203. So this should tell you right away that it's square. Okay. So that means that this HSS, okay, is 8 inches by 8 inches. That's why it's 203. So it's 8 inches this way. This is 203 by 203. And if you see two different dimensions, then right away you know that it's a rectangular one. And of course, the longer one is the longest side of the rectangle. And if you only see one dimension for HSS, what does that tell you? If I see 203, if I see this as a HSS, 203 by 9.5, what does that tell you?
It's a circle.
It's a, yeah, exactly. It's circular. That's all that means. So that's right away if you can tell, is it square, is it round, or is it rectangular? You just look at these two dimensions. If it says HSS 203 by 9.5, well, it's a circular HSS, okay? Now, the only, oh yeah, the 9.5 is a wall thickness, okay? It's the thickness of the wall of your HSS. Keep that in mind, and of course, that's in millimeters. That's what I wanted to show you. Now, again, 20 MPa concrete, Fy is 900. Now, so the area required, 1,550 divided by 0.85 phi c, Fc prime, and of course, I end up getting the area required of 140,000 square millimeters. Now, very simple, it's square, therefore I'm going to make it square. So I'll take the square root of that, right? And I end up 374. And look at this, even the textbook used 380. In other words, use multiples of 10. I'm glad the handbook is smart. They also recommend using multiples of 10. So that's one thing I like about this one. So you take the square root, and that's because it's square. Now, the only difference is that here, okay, the end value for HSS, you have to go halfway through the wall thickness. I don't know if you can see that, okay? Okay, so this is 9.5, okay? So you notice that you have 203, this is 203 here, okay? So in other words, from outside to outside, okay, you have 203. And what they're doing is that they're subtracting the wall thickness, because if I take half the wall thickness here and half the wall thickness there, you're actually going to half through the wall thickness to get the value of your cantilever. So therefore, it's actually subtracting a whole thickness. So that's what that is, okay? So you're calculating your thickness right from here to there, and the same thing here. So since you have half on this side, half on that side, well, it's just like having the whole wall thickness of 9.5. That's all you have to keep in mind for HSSs. Remember to subtract the wall thickness from your overall size of your column to calculate your N or your M. Okay, that's what you have to do. And of course, this minus this gives you 93.3, and therefore N is equal to M. They're both the same values. So here you go. So now I can simply go ahead and calculate TP. 26.3. Okay, so therefore this is, like I said, 380 by 380, and now of course I have 26.6. So there I need, okay, so if I go here to the material, 26.6, I shouldn't use 25. That's not 26, so I shouldn't use this. So I am here. Okay, so my second preference would be to use a 28 millimeter plate, and my first preference would be to use a 30 millimeter plate. And that's what I would specify in my drawing. Second preference, 28, first preference, 30. And let the guy who's bidding on the job, who's going to be doing it, make sure he gives you at least 28. And if he puts a 30, you find that to be quite acceptable. And therefore, you put first preference is 30 millimeters, second preference is 28. And that's what I would specify in my drawing. Okay. And like I said, if I would end up with 29.2, I would just put 30 millimeters. I wouldn't even put first preference. I would just specify 30 millimeters. But you can give the guy the option to go find some 28 millimeter plate. If he can find it in that grade of steel, that strength of steel, he's more than welcome to use it. HSSs are much easier. Now, the only thing about HSSs, you better make sure that you have space here, your edge distances, to be able to put in your anchor rods or your anchor bolts. Okay, that's all you have to worry about. And normally the edge distance here, okay, is you should give yourself 35 millimeters. That should be your edge distance. Okay, and therefore if I take 35, that leaves me ample room to be able, because don't forget guys, when you're putting these anchor, here's your hole. Okay, don't forget that there's a washer that is much bigger than your nut. Then there's a bolt hole. There's the anchor rod or the anchor bolt. And then after that, there's a nut. And when we get into connections, you'll see this a little bit more clearly. But don't forget, the washers that you usually put before you put the nut down, Okay, they're bigger than your nut, so therefore you should have ample room to be able to put your washer around your anchor hole, and then put your nut on top of it like this. Okay. So I hope, anyways, this is called the nut. That's called the wash, and of course that's your anchor bolt or your anchor rod, whichever one you want to. Okay. Any questions here? So you can see that when it comes to square HSSs, they're not very complicated, straightforward. Okay, they're N and M are the same. The only thing you have to remember is that when you're calculating your M and your N for HSSs, take away one of the wall thicknesses when you're calculating it. In other words, take your overall size, take away one wall thickness, which is actually going to halfway here, halfway there, and that's how you calculate the N. Okay, before I move on, does anybody have any questions? How are we doing time-wise?
We're good. 9:20.
9:20. Oh, we're really good. Okay. Now, guys, you'll get in situations, this, I'm giving you this more for your general information. You're not going to get tested on this. The next one is what we call lightly loaded plates, okay? Sometimes you're going to calculate that the area required your concrete is even smaller than your section, okay? So check, oh yeah, check deflection. We check deflection's okay. I forgot to tell you, always check for your deflection, which is okay. Now, when you have what they call lightly loaded base plates, for lightly loaded base plates where the required bearing area is less than or about equal to the area bound by the column. In other words, you calculate your area and all of a sudden it's within either the size of your column. So in other words, you got no projections. You know, like you don't need to have, you don't have any M's or any M's. If you use the other formula, it will give you an unrealistic value for N or M, okay? So what they're saying here is that when you're calculating the area, and if it happens to be smaller than the area of your column, it's considered to be a lightly loaded base plate, and therefore you cannot use that other method, okay? Okay. The above method does not give realistic results for the base plate thickness, and other methods have been proposed in the literature. And then this is one guy that developed this in 1970. It's still used today, okay, when modified by limit state design, okay? So this is how you calculate the thickness of the plate for lightly loaded columns, okay? Now, we'll go through each variable. Don't worry about it. BR, of course, is the bearing resistance of your concrete. That doesn't change. Beta is calculated by this formula here, 0.75, 1 plus 1 over lambda squared minus lambda 2. What is lambda? Lambda is 2d times b, okay? And of course, D is the column depth, B is the column width. In other words, those dimensions don't change, okay? So that's how you calculate lambda. So once I know my column size that I'm going to be using, I know my D value, I know my B value, I can calculate my lambda. Once I calculate my lambda, I can calculate my beta. I know what my BR value is, and therefore when I put everything in here, it will give me the thickness of the plate. And that's what you have to do. So, okay, it's not very complicated, but this is what's recommended to calculate what they call lightly loaded base plates, okay? So now, a W200 by 31, reasonable column. Okay, this is a reasonable size column, a W200 by 31 column subjected to an axial force of 320 kilonewtons. Is supported by a concrete foundation wall, which is 30 MPa. Designed the base plate assuming the steel being 300. Okay, so now I go and look for a W200. I'm going to write it down, W200 by 31. Of course, what I'm looking for is always the B and the D values when I'm doing these calculations. So I go here. And I don't know if you guys notice it, but the way these tables do is they start with the widest one and they keep going down to size until you hit what you want. So you're looking for a W200 by 31. So here I am, okay? And of course, this is the cross-sectional properties, and the next one is the geometric properties of the section. So I go over to the other side where I see 31. And this is where I get my B value, my D value 210, and my B value of 1. So 210 and 134. So there's my D and there's my B, okay? Okay, so I get 134 and 210. That's what I get from the Y-plan shapes, okay? Now, area. So CF over 0.855C. So if I do this area, I end up with 19,306 square millimeters. Now, if you guys multiply this by this, you'll see that this area here is greater than that area there. So that means that when you're looking at your column here, okay, this is the area of B times D, okay? And the area required is smaller than your column. So how am I going to be able to put a plate there? How am I going to be able to weld my plate? How am I going to be able to weld my plate to to my anchor bolts? You understand? And so what they're saying is that in this case here, this would be considered a lightly loaded column, a lightly loaded base plate, I should say. Okay, the surface area of B times E is 2. So therefore, the area of the column is bigger than the area of the plate. It doesn't make sense. I mean, nobody's going to put a base plate where the column can't even sit on the base plate. So you have to do something. So the surface area of the column is greater than the area of the plate. Therefore, you wouldn't even be able to calculate your N or your M value, and so on and so on. So what we do now is, because this is the situation, we know that we are under a lightly loaded plate, and therefore I will use the other method of calculating the T. Design base plate as a lightly loaded base plate. Okay, so lambda is 2D over B. This was the, okay, and this is where we get the B and the D value. Okay, so there's my lambda value. Like I said, once you get these two values, you get your lambda value. And if you remember, the beta value is the square root of 0.75, 1 over 4 lambda squared minus 2 over lambda. And of course, I just have to be careful with the math here, square this, and then do this, and then subtract this from it. So if I did this correctly, I think you guys should would somebody double check, just in case I made a typo. But 1 over 4 lambda squared. Okay, so square root of that, and then 1 over 2 times lambda. I think that, I'm sure this is pretty good. Does everybody concur with this number? Is it good? Because if I screw this up, the whole thing is screwed up. I'm not sure. Anyways, if you guys find a mistake, let me know. Now, BR, of course, 0.855 C phi. I should have put a C here. This is phi C. Okay, I'm sorry. This should be there should be a C there. 0.65. So I get 16.61 MPa. There's a typo there. That should be phi C, not phi. Okay. And now I've got all my values. Now I can go calculate my TP value, because I got my value of beta, I got my value of BR, I got my value of B. Okay. So I simply now, this is phi for the, like I said, that's a typo, guys. There should be a C there. This is phi C, always, okay? And therefore, now that I got all my variables, I put in the equation, make sure I do the math correctly. I end up with a TP equal to 14.8 millimeters. And of course, at 14.8 millimeters, if I go to the plate material, I would use a 60 millimeter plate. And again, you should check the T over 5, which should be ample. I mean, you can't even check the deflection here because you don't even know what the M or the N is. So guys, so you're using a 60 millimeter plate. Now people say, well, what would be the area of the plate? Well, then that would be governed by the geometry. Let's see. Okay, so basically what you're doing now, okay, so people say, well, what am I going to use for B and D? Well, what you do is you put your column down, right? You put your column down like this, okay? Put your column down like this, okay? And then you know that, you can come here like this, you can come here like this, and then you basically, you know what this dimension is here, you know what you need here to put your, like I usually leave here, I usually leave 70 millimeters. I usually leave here at least 70 millimeters. In other words, 35 times 2, okay? So if this is D here, D was what, 210? 210 plus 140. So I would make this 350. So I would let the geometry of my column, this is 136. So I would say that's be 140 plus 7 plus 140, I would make this 280. And that's how, and then of course, that would be the size of my plate. And then I would specify a thickness of 16 millimeters. Okay. Now, in the assignment, I'm going to ask you to draw. Okay, I'm going to ask you to draw the optimization of your base plate in the assignment. So get into the habit. What I mean by draw is you show me a base plate. You show me the, like that there's what's the shape of the column that you put on. You give me the size of the column that you have, the size of the plate here. You show me where your bolt holes are. And of course, we're going to get into this, but you're going to learn you're going to learn these welding symbols that you're going to be welding all around, okay, and so on, okay. So I expect to see that drawing on the exam, and therefore I think in the solution next week, when I say draw it, you'll see how I drew it, and I'm leaving it up to you so that you can guys get into the habit of drawing the plates. Okay, I want you guys to start visualizing it and start making sketches, okay. And I think that's basically it. So guys, I strongly recommend that you try assignment number 4 and especially try drawing the sketch so you can see if you're on the right track. If I don't want it to be exactly the same, okay, but do the assignment. And like I said, next week I will give you the solution to the assignment, and hopefully, and that's it. Unless there's any questions. So let me stop sharing. I'm going to put this on pause. Does anybody have any questions?
No, not at the moment.
We're 10